Welcome back. Good afternoon. We'll start with this final presentation in order to close the series of presentation for today. So now we have my colleague Andrea Cipollina that will present the multi-feed plug flow reactor for selective recovery of magnesium and calcium from brines. And of course, you have 20 minutes or so to deliver your presentation, and then I'll further inform you about the rest of the.
You give me a sign.
Of course. So we are perfectly on.
When I will be at the third slide and I have 5 minutes left,
No.
Okay, so good afternoon,
minutes.
colleagues and friends. Yeah, I will close this first day of the Fast Track School talking about a technology that we have developed in the last 10-15 years here at the University of Palermo, which is the multiple feed plug flow reactor for selective recovery of magnesium and calcium from brines. But actually the technology can be used to recover these elements from any kind of solution containing magnesium and calcium in ionic form. But to start, I would like to focus on why we need this technology within the salt-to-water integrated treatment chain. We have discussed this morning about photovoltaic reverse osmosis, about brine valorization, about membrane distillation for concentration. Guillermo skipped one important information, that we can achieve those concentration only if there are no scaling agent, which is calcium and magnesium containing carbonate. There was, in one slide, but this has to be mentioned very carefully. So if we want to reach almost saturation condition, we need to remove first the bivalent cations present in the brine. And this can be done by any crystallization technology, but if you precipitate them in a normal crystallizer, you risk to have a product that is not marketable. What we want to do, what we want to demonstrate, is that we can perform a selective separation, selective fractionated crystallization to recover valuable minerals. And in particular, among the two minerals we are talking about, magnesium hydroxide is certainly the most interesting. Magnesium hydroxide is a quite common product used in many different industrial sectors as a flame retardant in polymeric industry, as a pharmaceutical or nutraceutical ingredient, for environmental protection, as it is a weak alkaline species, but it is bivalent, so it's safe but very effective in neutralizing acids. It's also used as a precursor for magnesium oxide catalyst, but it is used as a precursor for many other materials, for refractory industry, for metallurgical industry, and so on. And the point is that currently there are only two sources of magnesium hydroxide. One is mining activities. The other one is recovering it from seawater using a dolomitic lime. The problem is that magnesium, and magnesium hydroxide is among the many different species in which magnesium is present, has been classified by EU as a critical raw material, both in terms of supply risk and in terms of economic importance. The economic importance, as I said, is related to the many different applications where you use magnesium hydroxide. But the supply risk is related to the fact that most of the product imported by EU comes from China. The rest comes from Russia. In both cases, not a nice situation for Europe to be dependent so much for magnesium imports from these two countries. And therefore, Europe is pushing a lot for the development of technologies able to recover magnesium from different sources. And of course, our case is one of the best ones, no? Because brines are available basically everywhere. In the whole Mediterranean region, we have brines available, and this brine can be a useful source of magnesium. Now, I would like to give you some fundamentals on reactive crystallization principles, and then I will go with the description of the technology, the history, so the chronological development steps we have followed, and the final application. Crystallization is a well-known separation process, at least for chemical engineers, it is a well-known process. It is used to separate a solid phase from a liquid solution, which is often called mother liquor. And this separation occurs thanks to a physical phenomenon, normally it's a physical phenomenon, in which the solution is made supersaturated. That means we go into a scenario, situation in which concentration is above the solubility of the species, and this leads to the formation of crystals of solids that precipitates. In particular, when we have a concentration in the solution higher than the solubility, we say that supersaturation index is above 1, and the solution is supersaturated. In reactive crystallization, the condition of supersaturation is achieved by mixing two different solutions. One is the one containing one of the reactants, the other one is containing the other reactant or an antisolvent, a species that reduces the solubility of the first solute that has to be precipitated. But we have to pay attention to the fact that crystallization comes with a number of complex phenomena. Nucleation, that is the first step to form crystals nuclei. Crystal growth, that allows the growth of crystals in the crystallizer, but also other phenomena such as aggregation, which is a phenomenon leading to the assemblage of particles with very strong bonds between them, creating particles that are very difficult to break, or agglomeration, in which we again put together, assemble different particles, different crystals, or different aggregates, but with loose bonds. And in this case, these agglomerates can be easily broken. But phenomena leading to the formation of aggregates or agglomerates dramatically affect the nature of the suspension that we are going to create in our crystallizer. And going back again to the definition of supersaturation. So we are basically going from a situation in which the solute is soluble to a situation where we have a concentration much higher than the solubility, so supersaturation. And when this is generated by a chemical reaction, we talk about reactive crystallization. And a good example to talk about reactive crystallization is the case of magnesium hydroxide, that is our case of interest. We have magnesium ions. We can add oxidryl ions by means of adding an alkaline reactant. And this leads to the formation of a solid phase, which is the magnesium hydroxide solid phase, which is our product. So in this case, the supersaturation is not generated by increasing the concentration of magnesium, but just by adding the second species that reacts, forming the insoluble solute. With reactive crystallization, supersaturation can be defined in different ways, but this is a very common way of defining it. So it's the ratio between the actual concentration of the two reacting species, power to the stoichiometric coefficient, divided by the solubility constant of the species. If this number is above 1, it means we are in a supersaturation condition. We will have precipitation of magnesium hydroxide. These phenomena have been studied quite a lot in the literature because there is a lot of interest in recovering magnesium in the form of magnesium hydroxide. And just to give you an example, there are literature works analyzing the effect of mixing magnesium chloride solutions, either synthetic or real ones, so containing also sodium sulfates and so on, with sodium hydroxide solutions, leading to the formation of crystals, which are typically very small, in the size of 50 nanometer up to 100 nanometers. You can see from these electroscanning microscope images, we have very small crystals. This is one recent work we have published. But the reality is that if you don't look at the electron microscope, but you look with a simpler analytical technique, how the suspension looks like, that means, for example, with a laser granulometer that only looks at the macroscopic size of particles, you see a very different situation. A distribution of particle size which goes from 1 micron to 100 microns. Here we go back to the definition of aggregate and agglomerates. So in this analysis, we don't see crystals. We see aggregates and agglomerates, which are bigger and cannot, distinguished by crystals in a simple analytical tool like a granulometer. Okay, now all that to say that in order to develop a proper solution, a proper technology to recover magnesium hydroxide, we need to develop something that properly addresses all these goals. High recovery of magnesium and calcium, because we don't want to leave magnesium and calcium in our brine. But at the same time, high purity of magnesium hydroxide, which is our main product. And we need to understand how to generate a high purity product. But then, which is the most complicated part, triggering crystals growth and control aggregation, agglomeration phenomena. Okay, that has been the objective of more than 10 years, probably 15 years research activities in our laboratory, in our institution. And just to show you briefly, which have been the developing step of this technology, everything started, more than 10 years ago, in 2010, 2011. This was a paper we published at the end of this experimental campaign, where we wanted to investigate the integrated production of fresh water, sea salt, and magnesium from seawater. But in a quite peculiar scenario, because it was not what we are studying in Sol2Water project. That project was more site-related project, because we have, maybe go to the next slide first. In Trapani, the west coast of Sicily, we have a very peculiar situation with a thermal desalination plant, which has been now stopped. Well, a few years ago it has been stopped, but at that time it was operating very close to a saltworks. Saltworks is a place where sea salt is generated with natural evaporation by sun and wind. And thanks to this proximity, we could start in 2009, 2008 or 9, a real environmental experimental campaign using the brine from this desalination plant to feed the saltworks. Everything worked very well. And this was the start of this long adventure, this long experience, because we could implement the full integrated cycle starting from an existing desalination facility, an existing saltworks facility. This was already there at industrial scale, so production of fresh water, production of food and industrial grade sodium chloride. But what we did was to develop technologies to further exploit this byproduct, this waste solution. The exhausted brine called bitter from saltworks for minerals recovery, and then also something which is not really related to our project, production of electricity. At that time, we had the repower project ongoing, production of electricity from the saturated brine. And during these years, we found out that these brines were extremely rich in magnesium, but much more rich than seawater and even of a desalination brine. We are talking here about 40-50 grams of magnesium as an element per liter of solution. So we are talking about 20-30 times more than seawater. So we started with very simple experiments, just using a blending process in a laboratory beaker with some stirrer and thermostatic bath, precipitated our solids, analyzed our solids, but I'll go very fast with that, and obtaining very nice results in terms of purity, recovery of our product. In particular, in some conditions, we could achieve purities of magnesium hydroxide up to 99%, but the problem was the control of crystals morphology. And crystals morphology can be a quite important point to address when you want to sell your magnesium hydroxide, because there are industries willing to have very small crystals because they have a very high surface area to make it very reactive, or industries, which are the highest value industries, that want very big crystals with a low surface area, which is the case of flame retardant industry. And therefore, we started analyzing different approaches. Okay, that was done in the lab, easy, but less significant in terms of implementation at the industrial scale. We tried to study different configurations, like a P-mixer reactor, where we mix the two solutions in a very narrow channel, where we have extremely high mixing efficiency, ultra-fast mixing, but also very high supersaturation levels. We induce a very fast crystallization process. But we also used different systems, like semi-batch systems, in which we have a stirred tank, where we added one of the two reactants, while the other is in the reactor itself, or we can add both reactants in this reacting system, little by little. These systems are characterized by a relatively good mixing, because we have a stirred tank, but medium or low supersaturation levels. Do these different conditions affect the final product? The answer is yes, of course. Otherwise, I would not be here explaining you.
Andrea, 5 minutes.
No, you're lying.
No.
Okay, yeah, I'll go faster. The answer is yes. Super fast mixing and high supersaturation leads to very small particles, very small crystals. The semi-batch reactors leads to much bigger crystals, which resemble much more to the highest value commercial product that we have, the Magnifin, which is a magnesium hydroxide for flame retardant application. From this, we started thinking, how can we develop a technology which can be worked at industrial scale, so to be continuous, to be operated under steady state condition, but replicating what we have in semi-batch reactors. We have transformed what happens with time in the semi-batch reactors in something that happens along the space. So a long reactor where the injection of the reactant is occurs, let's say, distributed in multiple ejectors, multiple nozzles along the length of the reactor. So we started working on this idea first on the laboratory scale and then to the pilot scale. And of course, when we realized this idea was nice, interesting, and it worked, potentially applicable at industrial scale, we also thought about IP protection. We deposited a patent. We have now a world patent under examination. But in 2017, we also decided to constitute a startup company, Resources, which has been now in the last years an important partner for all our research activities on this topic, whose core business is to develop technologies for magnesium recovery from brine. And now, in the last part of my presentation, I'll give you a very quick overview of where the crystallizer we have developed has been applied. In the first example is the zero brine project, where we wanted to recover magnesium and calcium in fractionated way, but from a very different type of brine. This brine was very rich in calcium and much less rich in magnesium. And we could do it in two separate precipitation steps, but very similar in principle to what we are going to do in Sol2H2O project. These are pictures of the first MF-PFR pilot here in Palermo, and the same pilot when it was brought to the Netherlands, where it was tested in a real environment with the real brine. And these are the first results. Very good stability of the pilot on time. And so you cannot read for sure the numbers here. The two steps lead to very good results. Magnesium purity above 90%, calcium purity above 95% in average, and quite good recoveries. But a purity above 90% is good, but it's not enough to make it commercially viable. So we try to understand why we have this low purity, because in this case, there was a huge amount of calcium, and there was also a lot of carbonates and bicarbonates in solution. As long as you increase the pH of the solution, calcium carbonate starts precipitating. So we also assessed kind of simple pretreatment to remove bicarbonate and carbonate by CO2 stripping in a column, and results were actually very, very positive. Just look at these ones. The purity was 91, 97, 98% without CO2 stripping, but after CO2 stripping, in the very same condition, the purity was always above 98%, which was a very important achievement. Now, whether we will need in salt to water or not to make the CO2 stripping, we will find out, but just in case, it will be a simple process that we can easily implement. Other project in which the technology has been implemented, water mining, Giorgio has already explained to you this morning.
I think it's
So
interesting.
red and red from the nanofiltration goes to the MF-PFR. So it's bivalent rich solution with a concentration of magnesium around 4 grams per liter and a bit less of calcium, and we can achieve the fractionated crystallization. Then we also have an EDBM unit to produce alkaline and acidic solutions. The alkaline one is actually used in the same reactor in order to perform the precipitation, while the permate of the nanofiltration goes to an MED and then evaporating basins to generate sodium chloride, high purity sodium chloride. And again, these are pictures of the pilot plant, which has been fully containerized. We also had that, in that project a drum filter for the separation of solids from the slurry. The stability with time was assessed quite good. This is just the final cleaning phase. And also the performance in terms of purity of magnesium hydroxide and removal rate were very, very good. Purity always above 95%, but reaching 99% in some conditions. And removal rate, which were very close to 95 to 100%, which is in general enough in order to avoid any further precipitation of calcium and magnesium species after this treatment. The technology has been used and is being used also within the circular mine project for magnesium extraction from bitterns coming from saltworks. So we are going back now to the origin of this long excursus, because in the circular mine we are valorizing the bittern coming from Trapani saltworks. And the first step is the extraction of magnesium. During the tour, we will see all the pilot units already installed and integrated. I will explain you more about each unit with the help of our collaborators. So I will just skip for now just a nice picture of Trapani saltworks, where you should definitely go sooner or later. And this is the 3D drawing of the, let's say, the third generation multiple filter flow reactor, which had in this configuration a very complex arrangement because of the very high concentration of magnesium in this specific case that requires a number of recycle loop and pre-dilution steps.
Andrea, the picture you have shown about Trapani is also related to the circular mine.
Yeah. It is the site where we, at the end of the project, or in the last 3 months of the project, we will ship our pilots and test the pilots in a real environment with real bitter from saltworks. No, there is one last project I was forgetting. It's a revised project coordinated by Aqualia in Tenerife Island. We will install, well, they are installing a big pilot facility for the valorization of brines, and we will give our contribution by providing the crystallizer, but also providing supports for the design of solar ponds that will be have been already constructed, solar ponds that are needed in order to concentrate the brine exiting from the nanofiltration unit, remove limestone and gypsum, so remove calcium basically, recover sodium chloride, and eventually have our magnesium-rich concentration to be valorized in our crystallizer. So in conclusions, recovery of magnesium and calcium from desalination brines is possible, as demonstrated in several scenarios. The control of solid purity, morphology, and granulometry is a key factor in order to produce marketable compounds, which is a very important point if you want to scale up technologies. And researchers in UNIPA have developed the MF-PFR technology able to control reacting conditions, which significantly affect the features of solid products. We have tested this technology as shown, and we are still testing it in ongoing projects with different brands.
But soon at 4 o'clock this afternoon, you will see actually the whole integrated chain in the big lab that is next door to us.
So I would like to thank you, but thanks all the people who have contributed. I would have needed other 5 slides to put all the pictures of them, so I just
It's a very long
gave up because it's a very long activity, and really about 50 people in these 10 years have contributed
at least
to the work.
Okay, so
now
we are still on time, maybe for questions or curiosity. Isabel, please.
Maybe I'm getting far away of the
topic.
So being conscious that the brine valorization is quite a huge challenge and important. From all the let's say ionics or ions that you have inside the brine, what is the most important nowadays to put into back in the market, or that would be called to you?
So, well, Angel has replied already a similar question. It, first of all, strongly depends on geographic conditions, and it's very site specific. He gave a very good example. In general, if we only have to look at the economical value, I think magnesium is the highest in terms of economic value and concentration, because sodium chloride ions, magnesium ions, and sulfates are the most abundant species in seawater. Sodium chloride is very abundant, but the value is very low. Just to give you some figures, 1 ton of sodium chloride can cost 40 euros or 50 euros. 1 ton of magnesium hydroxide can cost up to 2,000 euros. Of course, it depends. I'm targeting the highest value market. But even if you go to the lowest value market, the price ranges from 500 to 1,000 euros. So it's still more than 10 times higher than sodium chloride. That makes of magnesium the most relevant, economically relevant element, even more than water itself, probably. Sulfates, we have addressed it within water mining projects, or we have tried to address the objective of recovering sodium sulfate using adaptive freezing crystallization, which at the pyroscale didn't work properly, but our colleagues in QDERT, they are working on the technology for recovering sodium sulfate. But this is, of course, a good option. And sodium sulfate is also one of the target minerals within circular mine project, because after recovering magnesium, lithium, and other trace elements, sulfates still remain in the solution with a lot of sodium. So there is a possibility to recover it using the same basins that we use to recover sodium chloride.
But for sure, Andrea, there is this huge problem, the geopolitical factor, especially these days, and so the so-called the critical raw material within the European Union, so statements have been made, and there is a huge issue behind. Of course, the availability in brines is different depending on the concentration. But the challenge is that the European Union is in trouble. So we know perfectly that the situation with magnesium, the market is, increasing the demand, and the forecast they say that it will continue, but there is a shortage because all of the magnesium comes basically from China and Russia, where it used, in old times. Now it's and lithium comes from the lithium triangle in South America, and Chile, Argentina, and so that there is a problem. So I think it's something that. Sorry, Paul. But anyway, we still.
Angela has a question.
Yeah.
I have a couple of questions. The first one, have you considered, are you working on different types of magnesium as magnesium oxide or magnesium metal for
No, we are of course thinking of that, but the technology requires, well, for magnesium oxide, we are not working on that just because it is a very simple step. You just require to remove water by heating up the minerals. It's a well-known process, but it is energy intensive, and therefore it's something that we leave for the real scale up in case we will need to produce magnesium oxide. Metallic magnesium is really a fascinating topic. And
I mean, the other compounds would also.
yes, magnesium chloride, and we are working a lot on the pharmaceutical, nutraceutical sides to produce organic salts of magnesium, magnesium citrate, magnesium stearate, because even in small quantities, they have very high values. But there you require a different kind of approach, fine chemicals, so clean reaction system, scenarios.
We are exploring.
But we are exploring. We don't have a pilot scale TRL.
And the second question was, I saw in the SolidWorks flow that you were producing sodium chloride food grade.
In the initial one.
Yes. With
Food grade, industrial grade. The food grade means 97% sodium chloride, at least.
Did you have any problems using industrial brine?
No, at least not in that case, because the desalination plant was basically run with very small amounts of anti-foaming, anti-scaling, which were food grade. And anyway, there was no evidence of these compounds in the salt itself. Keep in mind that saltworks are a kind of ecosystem. It's a bioreactor itself, where the natural organic matter can reach levels of 200, 300, 500 ppm. So we are talking about adding 2 ppm of antiscalant in the inlet seawater, which is probably partially degraded already inside the desalination plant, and it will certainly degrade or mix up with the rest of organic matter.
And did you find resistance from traditional ways, or because we
found a big strong resistance by the WWF Foundation. It's the authority somehow managing or protecting the natural reserve of saltworks of Trapani. But this is an oriented natural reserve. It means it has to be protected, but by integrating the presence of this natural reserve with an activity, industrial activity, which is the production of salt. And on the other side, the owner of the saltwork was extremely interested in this application, because in those years of experimentation, he observed an increase in the production capacity of the saltwork, that small saltwork of 30% or more, just by opening a different valve.
Yeah.
He was even saving energy because he didn't have to pump the water in the saltwork. He just took the brine pressurized, and getting an increase by 30% without doing nothing is, you understand, is not a very good result. But we analyzed the salt quality, and there was no variation. And apparently also the project was carried out with some biologists. Also the biological life in the saltworks did not change in terms of microorganisms, shrimps, Artemia salina, the small shrimps there. But according to WWF, it was an ecological disaster. So we don't know which is the truth.
That is
We haven't seen.
Andrea, we discussed it a lot. They consider again the natural result. Now the point is, are saltworks a product of nature or a result of nature, or are a result of workforce for hundreds of thousands of years delivered by mankind? I mean, so these are not natural places; these are artificial places. These are the very first demonstration of, let's say, the work made by man And in order to preserve this very special areas, you need to provide support with a lot of workers. If you leave the salt ponds abandoned to themselves, to nature, they will be destroyed. Maybe not in 1 year, but in 10 years, in 20 years. So there is a misconception about these places. These places resist only if there is the support of a huge quantity of man-hours every day of the year. So the balance should be clear. Without the support of, of the people, cannot say. But they say that, you basically can turn into disaster. I would say, let's lead to nature and see what will. And there will be no.
Yeah,
no
the
balance.
ecosystem will be destroyed
They will
by
be destroyed easily.
nature itself.
So the conservation of this ecosystem, this equilibrium, is only because someone is working there every day. And if we make small adjustments without observing any real variation.
Yeah, if Giorgio was not a professor, he would have been a lawyer for.
Because remember that we discussed, we went to discuss.
The temperature of the brine from the desalination plant was a bit higher than seawater.
Oh, yes, because it was
5 to 10 degrees more.
10 degrees.
But yes, but these effect disappeared very, very quickly because as soon as water evaporates, it cools down. And
So that would probably be the only argument from that.
Oh, yeah.
Because
temperature variation.
with our brine, then you can say that chemicals behave. But
No, but
chemicals of the temperature.
the brine temperature in sulfurs can be up to 40 degrees. So it's higher than seawater.
No significant.
I think there was also a discussion on the metals release and things like this.
Yes, but it was analyzed. I mean,
Exactly,
this
it was
analytically clear that there was no.
Maybe.
Yeah, you know what I mean. Yeah, but
Yeah. But
no, but we went to check all this.
In reverse osmosis plants, things might be different because normally washing solutions are mixed with the brine, and washing solutions contains a lot of chemicals. Then if you want to implement such a scheme with reverse osmosis, you need to split and you need to treat separately the clean solutions. But the brine itself should be safe.
Okay, Andrea, maybe
We need to do two things before breaking.
No. Yes, I think I have an announcement from Dominique that I invite you to come here. I think we have to provide a kind of form to fill in. Okay, so for the gender equality report, I guess, but please, it is for you to decide something.
So one of the tasks on saltwater is gender equality assessment. So I've sent you an email with a link to a Google form, if you can go there. The first one wasn't working, so I sent the second one. Okay. So even for the ones in the meeting yesterday, you need to fill it again, please, because I've improved the answers as we discussed yesterday.